So this is a problem where we're given information at 1 mole fraction for binary mixture in vapor-liquid equilibrium. So we're given the mole fraction, x1, we're given the pressure at a temperature of 42 degrees C, and we're also given the vapor phase mole fraction that's in equilibrium with it. And we say we can model this by the 1-parameter Margules equation. And the idea is we want to use the data at one point to calculate the parameter, and then we want to determine at the same temperature but a different mole fraction, what's the bubble pressure, and then also the mole fraction of the gas phase that is in equilibrium with the liquid. So what I'm going to do first is pause, write down the information that we know. Is always the best way to start a problem, is put down in symbols the important terms that we already have and what our unknowns are. So the first thing to notice is that the pressure at mole fraction of 0.35 in the liquid phase is greater than either of the saturation pressures. This means we must have a maximum in pressure as a function of mole fraction, which means this is a system that has a maximum pressure azeotrope. And we're going to model it by the modified Raoult's law, which is the mole fraction of liquid phase times the activity coefficient liquid phase times the saturation pressure, all of component 1, equals the mole fraction of vapor phase times the total pressure. And then we have the same type of equation for component 2. So what we're going to do is rearrange these equations, solve for gamma 1, substitute in the values because we're given all of the other values, x1, p1 sat, y1, and p, and solve for gamma 2, and then we can use those to get the parameter for Margules equation. So the 1-parameter Margules equation relates the excess Gibbs free energy over RT to the 1-parameter in x1 and x2. But the excess Gibbs free energy over RT in general is related to the activity coefficients. Well, we have all of these values, so we can solve for A. So when we substitute in the values, we get a value for A, 1.491. This is dimensionless. It's the excess Gibbs free energy over RT. We can then use this to calculate the activity coefficients at a different condition. And the equation for the 1-parameter model is that the log of the activity coefficient is equal to A times x2 squared for activity coefficient component 1, and then for component 2, the same A times x1 squared. So we're interested in x1 equals 0.85. So let's determine gamma 1 and gamma 2 using this parameter A that we found. So substituting in the mole fraction and the value for the parameter A, we get gamma 1 and gamma 2. This is for x1 equals 0.85. We can now calculate the pressure at room here. Pressure x1 gamma 1 p1 sat plus x2 gamma 2 p2 sat. So I make the substitution, I get a pressure 1.495. Really only have 2 significant figures, so I've written as 1.5 bar. Note this is almost identical to the pressure for the conditions we're given at the beginning, the mole fraction of x1 of 0.35, and this is because we have an azeotrope and we can have 2 values. So let's do one more calculation and look at that, and that's to calculate y1, x1 gamma 1 p1 sat over pressure. So I've substituted the values into the modified Raoult's law and calculated the vapor phase mole fraction of component 1, and then wrote it as 2 significant figures. And so the fact that we have the same pressure in 2 very different compositions is a result of the azeotropes. Let's pause and just approximately draw what this pressure mole fraction system would look like. So what I've drawn is the initial values were given, 0.35 for the liquid, 0.578 for the vapor, and we just calculated for liquid at 0.85, the vapor is 0.76. Then I've added in the saturation pressures, and so we don't know exactly what this curve looks like, but we know it goes through a maximum at some point. This is the azeotrope, and this is why we can have 2 very different compositions with the same pressure.